Wang from University of Buffalo, who's going to talk about closing the simulation to reality gap, robust reinforcement.
Okay, good morning, everyone. My name is Wang, and I'm a PhD candidate from University of Buffalo. Today will be my great honor to be here to share my recent research work on closing the simulation to reality gap, the robust reinforcement learning on the model uncertainty. So in this talk, I will first give a brief introduction on reinforcement learning and simulation to reality gap. And then I will talk about our research work on robust average reward reinforcement learning. And then I will give a brief summary of my research project during my PhD period. And then I will talk about my research and teaching plan. So let's first start with reinforcement learning. So the reinforcement learning aims to find an optimal policy that maximizes the agent's expected total reward by interacting with the environment. So consider this very simple example. A dog wants to do the reinforcement learning with interaction with the environment, which is a human. So he observed that the human threw out a branch, and if the dog take an action to make decision to fetch that branch back to the people, and the people will give the dog a reward or a treat. So the dog knows that if he catch back the branch, he will get a treat or a reward. So during this interaction, the dog knows that, okay, I need to fetch that branch to earn a reward. So basically, the reinforcement learning can be modeled as a Markov decision process. So in a Markov decision process, it has 4 components: a state space, an action space, a reward function or signal, and an environment or a transition kernel. So at each time step, the agent will first observe the current state and take an action. So the dog observes that the people throw a branch and he try to take action to fetch it. And the environment then translates to the next state and provide a reward signal to the agent. The agent then receives this reward signal and observe the current state and take the next action. So during this interaction, the strategy of the agent to take action is characterized by a policy function, which is a function mapping each state to the probability of taking actions. And the goal of the reinforcement learning is to find the optimal policy that maximizes the total reward the agent received during this interaction. So how do we measure the total reward during this interaction? The most commonly used reward criteria is called discounted reward. So under this setting, we introduce a discount factor gamma, which is less than 1, and we define the value function or the total reward to be the discounted accumulative reward the agent received. So as you can see from definition, it's defined as the expectation of the summation of the discounted reward during the time period. So the goal of the reinforcement learning is to find the optimal policy that maximizes this value function. So nowadays, the reinforcement learning has found wild applications in many areas. The most famous one including the AlphaGo, which beats the world champion in the games of Go. So in this problem, the state would be the situation on the board, whether it is black, white, or new at each intersection. And the action of the AI agent is to place one stone at a different situation. And the reward, of course, would be to win this game. So in this problem, an AI agent aims to learn a policy or the strategy to place the stone at the intersection under different situations and finally to win the game. So another famous example including autonomous driving, where an AI agent is trained to optimizing the driving control. So in this problem, the state would be the driving environment, for example, the distance to the nearby car or the current speed. And the action of the agent would be to turn left or right, to accelerate or brake. The reward, of course, would be to drive safe and smoothly. And the policy we want to learn is to control the vehicle in different situations. So we all know that the reinforcement learning has found very much application and show very impressive performance in many areas. But behind all this impressive performance, there is one critical assumption called which assumes that the environment where the policy is obtained must be identical to the environment where the policy will be deployed. So in some areas like video games or game of Go, this assumption is very easy to satisfy. But in more practical applications, this assumption may be too strong to hold in practice. So for example, let's consider we are flying a drone. So usually, before we fly in the drone at the seaside, we will train the fly the drone and train it in a well-protected training field. We don't want to directly fly it at the seaside, otherwise it will crash into the sea. It will be too expensive. So of course, the training environment cannot be exactly the same to the real environment. So these differences between the training environment and the real environment is referred to as the simulation to reality gap. So this gap or the differences between two environments will lead to a model mismatch, and it can result in performance degradation if we directly apply the policy we obtain under a training environment to the real environment. Because the environment are different, it may suffer from performance degradation. So actually, this simulation to reality gap widely exists in many areas of reinforcement learning or machine learning, and it exists for many different reasons. So one of the most important reasons is that the real environment is just too complicated to be fully captured by a simulation or a training environment. So there would be modeling error between the simulator and the real environment, and hence leads to a sim to real gap. Another reason includes that the real environment can be highly stochastic and non-stationary. So let's see we have a simulator that fully captures the true environment. And then we obtain the optimal policy under this simulator. And now we want to deploy our learned policy to the real environment. But since the environment is non-stationary, the environment has already changed. So again, the training environment we are using is different from the real environment we are deploying. So again, it leads to a sim to real gap. And of course, in the real environment, there may be unexpected perturbations or potential adversarial attacks that cannot be fully captured and handled by training on the training environment. So all of this reason can lead to a sim to real gap. So initial question here is, why does this sim to real gap matter? What makes it very critical? Well, actually, the high cost of failures in most of the applications of reinforcement learning makes this sim to real gap very critical. So consider the application in the agriculture. Let's say a farmer want to train an AI agent to help him to schedule pesticide. So in this problem, the environment will be highly non-stationary and stochastic. The situation will be different from every year. So and there is no reliable or accurate data simulator for the farmer. So he must learn from the previous data, the historical data. So in this case, the episode of the learner would be 1 year. So if he cannot, of course, the simulator he learned from the historical data is different from this year's situation. So there exists the sim to real gap. So if this farmer cannot handle this gap properly, it may lead to a crop failure, which is expensive to this farmer because it means that he has no money in during this whole year. These consequences of the sim to real gap can be more critical or dangerous in many other different areas. For example, in healthcare, if we want to train an AI agent to get better insulin management in diabetes, since for different patients, the situations are different. And of course, we need to handle this sim to real gap properly. Otherwise, it may lead to some dangerous consequences. So it is hence very important for us to close this sim to real gap. So there are many potential methods to close this gap. For example, we can use transfer learning, representation learning, or domain domain adaptations. So the idea of this method is to first learn a concrete representation of the training environment and to transfer such knowledge to the real environment, and hence to learn a policy that will perform well in the real environment. But during my PhD studies, I mainly focus on closing this gap by robust reinforcement learning approach. So the goal of the robust reinforcement learning is to find a policy that performs well under the model mismatch. So to give you an intuition, let's first compare the standard approach and the robust approach. So under the standard approach, we first collect some data from the simulation and construct a straightforward environment model. we then obtain the optimal policy under this constructed model, and then we can only deploy our policy in reality with crossed fingers. Because we don't know whether the simulation we construct totally is identical to the real environment, and we don't know whether the optimal policy we obtain will also performs well in the real environment. But in contrast, in the robust approach, after we collect some data, we will construct a conservative or an uncertain environment model. And then under this uncertain model, we will obtain the optimal robust policy. And then we can deploy our policy in reality with confidence, because as I will talk about later, the robust reinforcement learning will provide a performance guarantee of our robust policy in the real environment. So as you can see, compared from the standard approach, the robust approach will provide a theoretical guarantee of the real environment, and hence can close such a sim to real gap. So how do we construct this uncertain model, or how do we do the robust reinforcement learning? Well, actually, the robust reinforcement learning or the robust MDP is very related to the non-robust ones. The only difference is that in the robust MDP, we are now having an uncertainty set of the transition kernels instead of specific transition kernels. And at each time step, the environment can transit to the next state according to an arbitrary transition kernel belongs to this uncertainty set. So since the transition kernel is uncertain, we are taking a conservative approach in face of such uncertainty. So it means that we are considering the worst case over our reward over the uncertainty. So we define the robust value function to be the worst case or the minimum of the non-robust value function among all the possible transition kernels belongs to this uncertainty set. So the goal of the robust reinforcement learning is to optimize this worst case performance, or equivalent to.
So what is the transition kernel in given situation? What's the transition?
Yes, the transition kernel is like capture the transit of the environment. So if we go back to the very beginning, the MVP. Yes, so after an agent is taking an action, the environment will transit to the next state according to this transition kernel. So in the robust case, the transition kernel is not unique. So the environment can take an arbitrary transition kernel to the next state.
So what is transition kernel? It will take the next state, but transition kernel is what?
It's a distribution. It's a distribution over the states.
Some distribution.
Yes, it's some distribution over the state space and measures the probability of the environment transits to the next state.
Okay, so you have distribution in the standard case, but then you're not taking the uncertainty.
You mean the non-robustness case?
Yeah.
Robust case?
Yeah.
Yes. In this case, the distribution is uncertain. It comes from an uncertainty set. So since the distribution can be different, the environment can transit according to an arbitrary distribution. So we are taking the pessimistic approach or conservative approach to consider the worst case among all these possible transition of the environments.
So this is a somewhat different way in which we write that usually you have a transition matrix, but that is basically probabilities, right? Okay. So these ones are already probabilities. Then you put another set of probability on top of this probability.
You mean the are you asking there is a distribution of the
your transitions are already probabilities.
You mean the transition kernel may also follow us from some distribution?
I mean, is a distribution now.
But why do you use the kernel? The transition
It's just a name. It's just a name. It's not the kernel. It's just a name. I mean, normally we would write it out like S times A times S.
That's right. What the probability going from this state to that?
Yeah, and this is the same thing. You just did.
Okay. So standard one, they have the transition probability, but what you are doing, what's the difference? What you're doing?
Yes. So in standard approach, there is existing only one or specific transition probability, but in robust case, there are possibly multiple transition kernels.
Multiple transition probability.
Yes, the environment can transit from following an arbitrary kernel. So of course you can.
There's an uncertainty set.
Yeah, yeah.
Contains many possible distributions.
Yeah, the many distribution.
And you're uncertain which one is the one.
Okay, good.
So that's why he's minimizing.
Yeah.
Mhm.
So I think that's better. Yeah, thank you. So there are several potential probability distribution.
Mhm.
And so you want to pick which one to select, and then using that you go to next step.
Yes, yes.
Okay.
So the environment
Yeah.
transits following an arbitrary kernel.
Okay, yeah.
Okay.
Very good.
So back to your questions.
I'm fine.
Okay. Okay, so go back to the yeah, this slide.
Maybe if I may have a request.
Mhm.
Can you at some point identify, you presented a bunch of background,
Mhm.
so maybe identify where is your contribution.
Sure.
Okay.
I will.
This one is not yet. Good.
Yeah. I will get that paired very soon. So the goal of the robust reinforcement to optimize this worst case performance. And so here, let's talk about how do we construct such an uncertainty set. So let's see, we first have some nominal transition kernel from, for example, empirical estimation or designed by domain experts, which is shown this point. So centered as this nominal transition kernel, we construct the uncertainty set to be the distribution that is close to this nominal transition kernel, which is defined in this equation. So as you can see, the term R here represents the radius of the uncertainty set. It measures how conservative we are when we are designing this uncertainty set. If the radius is larger, it means that this uncertainty set is larger, and the minimum, the worst case over this uncertainty set will become even worse. So it means that we are more pessimistic or conservative.
So what's the Q and what is PAS? Are these distributions?
Yes. So the PSA here is the nominal distribution,
Okay.
and the
Yeah,
Q is some other distribution.
Okay, so finding D, the tail divergence or what?
Yeah, D here can be some any function to measure the distribution, like total variation, KL divergence, and so on. Yeah, so the main idea of we construct such an uncertainty set is that if we construct this set carefully, the real environment may fall into this uncertainty set. And so the performance of the real environment will be lower bounded by the worst case performance among this uncertainty set. So by optimizing the worst case performance, we are actually providing an optimized lower bound guarantee of the real performance. So this is basically the idea of the robust reinforcement learning. So there has been many previous related works on robust reinforcement learning, but most of these works can be divided into two categories. The first one is called model-based set, which means the nominal transition kernel is fully known to the learners. And in that case, we can solve the problem using robust dynamic programming. Another category is called the model-free setting, where the nominal transition kernel is unknown. We don't know the distribution, but we can obtain samples from these transition kernels. So there has also been many previous work on the model-free setting, but most of these works, they neither assume strong assumptions on the discounted factor, which means that the gamma should be bounded away from 1, or they are relying on a generative model, and their method can only be applied for the tabular setting, which means the problem scale is small. So in contrast, in our work, we developed a model-free robust reinforcement learning approach with convergence and robustness guarantee. We made no assumptions on the discount factor, and our approach can be applied to the large-scale problems with function approximation and policy gradient approaches. Another very important related area of the robust discounted reward is called the robust average reward reinforcement learning. So under this setting, we are considering a different reward criteria called average reward. So as you can see, the definition of the average reward is the average reward the agent received. And the robust average reward is defined to be the worst case. So the major question here is, why do we care about this average reward? So let's consider or recall this definition of the discounted reward. So as you can see from the definition, the reward received at each time step will be discounted by a factor of t's power of gamma. So since the gamma is less than 1, when the system operates for a long period, this term will become decay to zero exponentially. So it means that under the discounted setting, the long-term performance is not as important as the short-term ones. So it may lead to a myopic policy. But in contrast, the average reward setting considering the steady state performance, and hence it may lead to it will lead to a better long-term performance when the system operates for an extended period and makes the system more stable.
What is the advantage of doing the discount?
Yeah, I will discuss that later. I will come to that question very soon. So the goal of the robust average reward is to, of course, find the optimal policy for the robust average. Although the robust average reward is a very important question, there are very limited previous work on this topic. There's one previous work studied this problem under a specific uncertainty set called a bounded interval. And since they are only considering this specific uncertainty set, their result cannot be general or applied to other type of uncertainties. So in contrast, in our first work, we studied the robust average reward problem under the general uncertainty set, and we developed a fundamental characterization and a solution framework for the general problem. So this work has been gathered a distinguished paper award from the AAAI. And we further apply or generalize our approach to the model-free setting and develop a robust TD learning algorithm and a robust RVIQ learning algorithm. And all of our algorithms are provided with the convergence guarantee and the robustness guarantee. So next I will talk about my research work on the robust average reward reinforcement learning. So in this part, we first provide a fundamental characterization and a solution framework for the problem. We first propose the model-based method, including the limit method and the direct method. And we further generalize to the model-free setting and develop our two model-free algorithms. And all of our algorithms are theoretically guaranteed on convergence and the robustness. So let's first start with the limit method. So the idea of the limit method is to use discounted value function as an intermediate step to approximate the average reward. So this leads to the question why we want to study the discounted reward first. Well, actually, the discounted value function is very easy to compute, and there is no to compute such a discounted reward, there is no requirement on the structure of the underlying MVP. So in the robust setting, if we want to find the robust discounted value function, we just recursively apply this Bellman operator. So as you can see from the definition, this operator is shown to be a contraction with the parameter gamma. So it means that if we apply this operator recursively, it will converge to the robust discounted value function exponentially.
So in this one, what is the robust? Which makes it robust?
Yes, you can see from this sigma function. So the sigma function is defined to be the support function of this vector on this uncertainty set. So it measures the worst case of the next the performance of the next state. So if you compare with a non-robust setting, here it will be replaced by a specific transition kernel P times this vector. It means because in the non-robust setting, the transition kernel is a fixed state, you only need to consider the expectation of the next state under this specific distribution. But in the robust setting, we are not considering this minimum function, which measures the worst case of the next states.
So you're getting the minimization of this thing.
Yeah.
But then you just calculate that minimum once and say that that's my position.
Yes. So in the model-based setting, you can just calculate this part.
Calculate whatever you have to get. It's not really reinforcement. In fact, it's just solving the.
Yes. So basically, so as I mentioned, there are two categories. One is model-based and one is model-free. The reinforcement learning is more related to the model-free setting, where we do not have information about this uncertainty set. So it won't be easy to calculate this part because now we don't know what this PSA set is. So it cannot be calculated the minimum. So it is a model-free setting, which I will brief discuss later. But now
so this one, the situation you have. So what's the B here?
V is the value function or the discounted value function.
Okay, and what's the rho transfer, rho or P?
P is the transition kernel or the probability distribution of the next state. Yes.
So you get a transition for a particular state, you get transition
Yeah.
distribution.
Yeah, you have a
vector, and then you are finding the dot product of that.
yes. It's like the expectation of the value function.
And so you're saying traditionally they won't use that. They would just use the V. Or
They don't have this minimum. They only use this P transport V because the traditional there is only one transition kernel P.
so you're saying you find a minimum. You do a search or
Yes.
area. Can you explain a little bit more? Yeah, what does it mean?
It means that since the environment now can translate to next state according to an arbitrary distribution, so we are clear about, and the robust reinforcement learning cares about the worst case performance. So basically, this function measures the worst case expectation of the next
Okay,
state.
so you have a lot of distribution set A. So you take one particular distribution from set A, and then do another one, and then
Yeah.
find the minimum.
Yeah.
So how many distributions you have, and what those distributions are, or what's the?
Yes, it depends on the structure of this uncertainty set. So as I will introduce later, in some cases this structure is very clear, it's easy to compute. But in the most cases, this one is hard to compute. But we will develop a method to solve this issue.
So I have a question. In contrast to the typical discounted universe, discounted value function, are you not bringing back some elements of the discounted reward that you're trying to avoid? So we're taking the average reward.
Yeah.
And then in your office there, you have the discounted value function. And the question is, doesn't that take us back to discounted reward approach?
Yes, that's basically the idea of this limit method. We are using the discounted value function to approximate the average reward. Yes, so the limit method is based on the discounted ones to solve the average reward ones. Okay, so I will continue. So as you can see, the discounted one is easy to compute because it's a gamma contraction and it requires no assumptions on the MDPs. But in contrast, the average reward cares about the steady state or the limit performance. It is in general very hard to study, and it often requires additional assumptions on the MDPs like unit chains or other assumptions. So since the discounted one is easy to compute while the average one is hard, so the idea of the limit method is to use the discounted one to approximate the average reward ones. So this idea actually has been solved for the non-robust setting. So it has been shown that for any fixed transition probability or distribution and fixed policy, if we set the discount factor gamma goes to 1, then the discounted value function will converge to the average reward under the non-robust setting. So basically, under the non-robust setting, we can use the discounted value function to approximate. So the nature question is, does this result also hold in the robust setting? So the previous work studied this problem under a so-called bounded interval uncertainty set. So under this bounded interval uncertainty set, it implies that the number of the possible worst case transition kernel is actually finite. So basically it means that if you want to find the minimum of this function, you only need to consider a finite number of transition kernels. So in this case, this minimum is very easy to compute. You only need to consider a finite number of the possible kernels and then find the minimum. So, and since the minimum is taken over a finite set, the limit operator and the minimum operator can be swapped. So we swap the order and it implies the convergence of the robust discounted value function. But as you can see, their result is heavily rely on the structure of this bounded interval set. It cannot be generalized to other uncertainty sets. So to solve this issue, we first study the convergence of the non-robust discounted value function. So we showed that the convergence of the non-robust discounted value function is actually uniform on the uncertainty set and the policy space. And since the convergence is uniform, we can swap the order of the minimum and the limits operator regardless the number of the possible worst case.
Uniform convergence mean?
Yes. So let's go back to the. So in this result is called the pointwise convergence. It means that for any fixed p and pi, this one will converge to a function. But now the uniform convergence consider the convergence over a set of p and pi. So it basically means that the convergence rate over this uncertainty set should be uniform. So basically,
distribution.
yes. So let's see if we have let's see we have first have p1. This convergence rate is like a rate 1. And for another fixed kernel p2, it has a convergence rate rate 2. So the uniform convergence basically means that the rate 1 and the rate 2 are similar, and it's uniform among this uncertainty set and the policy space.
So I mean, that means uniform distribution. Is that argument for?
No, it's not a uniform distribution. It's
the same, or what would be it has to be pretty special? What does uniform mean? Same or they don't differ much? I think.
You can yes, basically means the convergence rate for each specific point is similar to each other. It won't be, let's see the distribution of the convergence rate is uniform. Or it's
uniform is used for distribution.
Yeah.
Yeah, so somehow you are getting some distribution and it's uniform.
Oh yeah. Basically, the distribution of the convergence rate is uniform.
Yeah.
Kind of like.
So then again you are doing the distribution and there's something going on to the limit and then that becomes distribution. Another distribution. Right? Kernels are basically distribution. That's what you said, right?
Yeah.
Kernels are distribution. Okay, yeah, that's fine. That's
Yes. So this uniform convergence actually implies that we can swap the order of these two operates and know regardless the number of the worst case. So it's by swapping the order, we show the convergence of the robust discounted value function, and hence we generalize the previous result in the previous work. And our result also implies that the robust average reward can be approximated by the discounted value function as the gamma goes to 1. So
can you go back? So in this one you are saying, so the left side you have that first you go to gamma as your discounted thing, right? So you want to change, gamma so that it was 1.
Yeah.
And then outer side you want to pick the distribution P or the whole thing.
Yeah.
Right. So now you're saying we can change it.
Yeah, we can change the order.
First is that you for the inner loop that you find the distribution out which
find the minimum and then take the
can change the
yes. So based on this result, we proposed our robust value iteration algorithm. So as you can see, the idea is that at each time step, we set the discount factor gamma goes to 1. And then we apply the one-step discounted Bellman operator. So as we discussed before, the discounted value function is a unique fixed point of this Bellman operator. So by doing this update of the discount factor and this Bellman operator recursively, we can show that our algorithm will converge to the robust average reward function, and the greedy policy we obtained will also converge to the optimal policy. So basically, it means that our robust value iteration algorithm actually solves the find the optimal policy and hence solve the average reward robust MDP problems.
So it means that the thing required or any change in the required that is captured by different distribution because searching or different distribution.
Yeah,
right? That's intuition.
Yes. So it's highly dependent on the structure of the uncertainty set and the distribution in this uncertainty set.
Where assumptions made on A, the uncertainty set so far. You adding that stuff that you need or just any distribution.
We are assuming that the MDP is unichain over this uncertainty set because I believe that our result can be generalize to multi-chain, but at the current stage, we only focus on the unit chain cycles.
So he's asking, so see, you're sampling the distribution from set A, right? So one is how big is set A? Like how many distribution you have?
It can be infinite set because if you define it using chaos divergence or other functions, it may contain infinite number of
Infinite number of.
yes.
Okay.
But in most of the cases, this function sigma p over this constructed uncertainty set can be solved by solving its dual form, which would be a let's say a convex optimization problem. So basically, to solve this function, it's very kind of easy or standard to solve the problem.
So other question was, I think he was asking, so is there any structure on the distribution? It can be any distribution or what?
Yes, we are. So back to the very beginning of the construction of the uncertainty set. So we are considering the uncertainty set defined in this function. So the R here is some radius, and the D function would be the some functions like.
But this is defining distant relative distribution, right?
Yeah.
So the question is, there are many probability distributions, right? So there's a Gaussian, there's a density, there's on the Poisson.
We don't.
Is there any assumption?
No. There's no assumption on this distribution. We only to set the the distance close is enough. We don't want it. We don't need it to be uniform or geometric or any other assumptions. That's
so distance between the original distribution where you are training the simulation and the what are the distance between what? The original
the center is some nominal transition kernel. It may comes from the empirical distribution.
Where you train and then you want to say the other distribution.
Yeah, just very close to this center. So if from the the big law of the big number, if the number is enough, the real environment should be also close to the nominal transition kernel. Yeah, this is basically the idea of the uncertainty set. Okay, so back to the convergence. Yes, so we showed the convergence of our algorithm, and as you can see, the convergence rate of our algorithm is actually 1/t. But for a model-based dynamic programming approach, this rate is kind of slow. But we will improve it later by developing our direct approach. So here I use some numerical experiment to verify the robustness of our algorithm. So we compare our robust value iteration with non-robust one for the non-robust problem. We train both algorithms under a nominal training environment, and we compare the worst case average reward with different uncertainty set. So it can be defined as a total variation type set or chaos divergence and so on. So we compare the at each time step, we obtain the output policy from both algorithms and compare their worst case performance. So as you can see, the orange curve, which represents our robust value function, robust value iteration, obtain a much higher robust average reward under the worst case than the non-robust method. So it means that our approach is more robust than the traditional value iteration method, and hence we can obtain a much smaller sim to real gap.
So what particular data set, what was the experiment done?
It's done on the so-called garnish problem. So the garnish problem is like the most general simulator in MDP. The state space, the action space, the transition kernel, and the reward function are all randomly generalized. So we do have some other numerical experiments on other environments like OpenAIG and other stuff in our paper. But here I only present the result on the garnish problem.
How much do you lose though? Because it seems to your approach is always gives you better, but it
Yes.
can't give you always better.
Yes, so basically we are now comparing the worst case performance, and our result is guaranteed to have.
How much do you lose on the other?
Yeah, if you consider, let's see, the performance under the nominal training environment, our algorithm is expected to lose to behave worse than the non-robust value iteration. How much I can't see exactly the number of this.
So let's say you have a you have something which is like you are walking, right?
Mm-hmm.
You don't expect it. So, but sometimes you can sleep on ice, right?
Yes.
Right. So your approach is gonna make the assumption that you are always gonna walk as if you are gonna sleep on every single, because you are minimizing always.
Yeah.
You are assuming the walk, so you are gonna like shuffle.
Yeah, in that case,
But that will not be the efficient.
yeah, because in our approach we are considering the conservative approach, but we can solve this problem by designing the uncertainty set, or to design the uncertainty set with a less radius. So recall the radius is defines the size of our uncertainty set. If the radius is small, it means that we are more confident of this nominal transition kernel. It means that the worst case will become slightly better. So in that case, if the uncertainty set is small, we can avoid this over conservative policy, and hence to solve the issue you just mentioned. Okay. Okay. So to summarize, in the limit approach, we developed the method to solve the average reward based on the discounted one. And since as we saw, the limit approach is based on the discounted one, so we cannot expect this approach will directly study or review the unique and fundamental structure of the robust average reward MVPs, because all the method is based on the discounted one. So it hence motivates us to develop the direct approach, which aims to directly solve the average reward MVP problems without using the discounted one. So to solve this problem, we first give a fundamental characterization of the structure of the robust average reward MVPs. So basically, we developed this optimal robust Bellman equation. So it states that if we can find a solution to this Bellman equation, then the solution G must be equals to the optimal robust average reward function. And the greedy policy we obtained from this solution would also shown to be an optimal policy. So basically, it means that if we want to solve the robust average reward MVP, we only need to solve this Bellman equation. So the question here is, how do we solve this Bellman equation? So recall that under the discounted setting, the Bellman operator is a contraction, so we can apply this operator recursively, and it will converge. But in the average setting, as you can see from the definition here, it's not contraction, and we have multiple fixed points. And so if we directly apply this operator recursively, the algorithm may even diverge. So to solve this issue, we develop our robust relative value iteration algorithm. So the idea of our algorithm is to, after we apply the Bellman operator, we will subtract an offset function to keep the iteration stable. And then we prove that this algorithm is a multi-step contraction, and hence will converge to the solution to the Bellman equation. So basically, we develop our robust relative value iteration algorithm. So as you can see, the difference here is that we offset a function fv, which is the offset function to offset the increase of v to keep the algorithm stable. And we further showed that our robust relative value iteration algorithm also converges to a solution to the Bellman equation, and hence it can find the optimal policy and optimal value function, and hence solve the problem. We also showed our algorithm converges exponentially, which is much faster than the limit approach. So due to the time limit, I will skip this part. This is basically similar experiments. We compare our relative value function value iteration with a non-robust one and compare their worst case performance. So to summarize, in the first part, we developed this model-based approach, which developed an essential relationship between the discounted MVP and the average reward MVP. And we proposed a fundamental characterization of the average reward MVP. And we developed the concrete algorithm with theoretical guarantees and on the convergence and robustness. So next, so the previous work is basically can be characterized as a model-based setting, which means we have full knowledge of the uncertainty set. But in practice, the model-based setting is actually kind of unrealistic. And in most cases, we have no information about the simulation. And sometimes the problem scale is too large. So it will be too costly to memorize the whole model. So it has encouraged us to develop our approach to the model-free setting, where we have no knowledge of the nominal kernel, but only samples from this kernel. So the idea here is that we need to construct an estimated robust Bellman operator to deploy our robust relative value iteration. But there are a few challenges here. So firstly, the Bellman operator is a non-contraction, but this one is similar to the model-based setting. We can solve this issue by using the offset function. And another question is the construction of this unbiased estimator of the operator can be very challenging and very difficult, which I will mention later. And we need also to show the convergence of our stochastic algorithm, because in the model-free setting, all of our algorithm is developed on the data or the samples we are getting. So it's purely data-driven. So we need to show the convergence of this stochastic algorithm instead of the deterministic one in the model-based settings. So here we develop our robust RVIQ learning algorithm. So as you can see, the differences between the model-based setting is that we will need to collect some samples from the transition kernel and estimate this operator H hat. And we then replace the operator by this H hat and run our relative value iteration. So H hat here is supposed to be some unbiased estimator, and FQ is the offset function. So the major question is, how do we show this convergence of this stochastic algorithm? So by doing so, we need to develop a deeper and more careful characterization of the structure of the MDP. So we further develop a more fundamental structure of the solution to this Bellman equation, and we then use the solution to the structure of this solution to characterize the equilibrium of the associated differential equation of our algorithm, and show its global asymptotic stable, and finally implies the convergence of our algorithm. So here the only remaining question is, how do we construct this unbiased estimator? So the straightforward MLE estimator from the sample can be shown to be biased. So more specifically, let's say we have some empirical kernel from the samples and construct an estimated uncertainty set centered at this empirical kernel, and define the estimated operator H hat as here. But it can be shown that this MLE estimator is actually a biased one. So it is more difficult to construct such an unbiased estimator. So to construct such an unbiased estimator, we adapted the idea of the multi-level Monte Carlo approach. So basically, we rewrite this function into an infinite summation of each level, and the AN at each level can be calculated or estimated unbiasedly. And then by choosing a random level, we can construct an unbiased estimator of it. So I will skip all the mathematics here. And we showed that for the most widely used uncertainty set, the estimator we construct is actually unbiased and has a bounded variance. And hence, it combining with the previous result, it implies that the convergence of our model-free robust RVIQ learning algorithm. So here we also use some numerical experiment to verify our result. So we deploy our model-free RVIQ learning with respect to different uncertainty set, and we plot FQ function here. So the orange curve in the figures show the update of our algorithm. The blue curve here is the baseline, which is computed using the model-based RVI method, which we discussed before. So the blue line here represents the optimal robust average reward function, and as a result shows, our algorithm will converge to this baseline, which means that our algorithm can converge to the optimal robust policy and the optimal robust average reward. It hence verified the convergence of our algorithm. So to summarize, in this model-free setting, we have no knowledge of this uncertainty set or the nominal transition kernel, but only samples from the nominal environment. And then we construct an unbiased estimator for the robust Bellman operator for average reward setting, and then we showed the asymptotic convergence of our stochastic robust RVIQ learning algorithms. So to summarize, we studied the robust reinforcement learning or robust MDP problem under the average reward setting. we develop a fundamental characterization and a solution framework for this problem, and develop two model-based dynamic programming approach with convergence guarantee, and further generalized to the model-free setting with asymptotic convergence. Okay, so next I will briefly summarize the research project during my PhD period. So during my PhD study, my research interest mainly focused on the theoretical and asymptotic, theoretical and algorithm foundation of the reinforcement learning, where I mainly focused robustness and the convergence of this reinforcement learning. I studied robust reinforcement learning in the presence of adversarial attacks, model mismatch, and outliers. And we also studied the convergence and the sample complexity, data efficiency of the reinforcement learning. I also studied the applications of reinforcement learning in control and management of the autonomous electric vehicles systems. So here is a brief summary of the specific project I've done. So under the robust reinforcement learning, besides the robust average reward ones we just discussed, I also studied the model-free algorithms for the adversarial robust reinforcement learning. We also studied the robust reinforcement learning under different scenarios, including the problem with constraints or with multi-agent sightings. I also developed a sample complexity analysis for the reinforcement learning algorithm to develop fast and convergent reinforcement learning. And I also studied the applications of the reinforcement learning to the AMOD system, the autonomous mobility on demand system. So that's enough for the past research. Let's now talk about the future, my research and teaching plan. So the automated goal of, my automated research goal is to build a trustworthy and effective AI system so that we human beings can use and utilize or rely on this AI system freely with no constraint, with no concerns, and with more confidence. So nowadays with the fast development of the AI system, the concerns of the AI is also simultaneously increased. I mean, you just search online for the questions like, will AI destroy the world? Will AI take control of humans? So my research goal is to develop the trustworthy and effective AI to enable our human beings can rely and use this AI freely with no concerns. So I aim to study the trustworthiness of the AI from several aspects. So firstly, I will continue my study on the sim to closing sim to real game and the data efficiency of the AI system. But I will not constrain to the robust reinforcement learning approach. I will also consider other approaches like transfer learning or representation learning and combine them together with robust reinforcement learning to develop a more concrete and universal approach to close the sim to real game. And of course, one of the most concerns nowadays when using AI is regard with privacy. It seems that nowadays our privacy is leaking every day when we, using a computer or searching online. So of course, it would be great importance for us to develop the AI system with better privacy protection because we don't want other users know the information about ourselves. So in this aspect, I will mainly focus on the differential privacy, which is related to federated learning or distributed learning. I aim to develop a distributed AI system with a better privacy protection. And I will also study the trustworthiness of the AI from many different aspects, including explainability, fairness, reliability, and so on. So the ultimate goal of my research is to review the foundation of the AI system instead of treat this AI as a black box where we just feed them data and train the model. So I aim to study the fundamental structure of this AI system and develop the trustworthy and reliable AI system to benefit our human beings to use this AI freely. So I will also interested in the applications of reinforcement learning or artificial intelligence in many different areas. So currently, I'm now working on a project to build an AI-based agent to assist the children with special speech or language-related needs. we aim to build an AI system to monitor, recognize, and help those children with special needs. So I'm interested in the application of AI in the healthcare, and of course I'm interested in the cyber physics system, including autonomous driving, and continue my study on the AMOD system. I'm also interested to unify the reinforcement learning with other areas, sub areas of artificial intelligence, including computer vision or NLP. So the recent success of ChatGPT or large language model shows the potential of the reinforcement learning from human feedback approach, where RLHF approach. So this RLHF approach showed a very impressive performance on the NLP tasks. So it is my future interest to study this approach on the CV text, and to see if we can using a reinforcement learning approach to solve the CV task problem and to improve the performance of the AI systems. And of course, there are many other related areas, including robotics, economics, and so on. So one thing I like about the UCF here is that no matter which topic I'm looking at, I can always find much potential collaborates. So for example, if I want to study the simulation to reality gap, I know Dr. Fu has been studying on the transfer learning or representation learning, and I know Dr. Baruni has been working on the imitation learning, and both of these approach can be used to close the sim to real gap. And hence, I'm looking forward to collaborate with all the professors here to conduct more research on this topic. And another example, if I want to study the differential privacy, I know Dr. Shivendu has been working on federated learning, and Dr. Mohsen has been working on cybersecurity. So I hence looking forward to collaborate with all of these faculties. And of course, I know UCF has a very strong and a big CV team. So if I want to study the RLHF in the method in the CV program, I know there's a lot of professors and students I can collaborate with. So here I briefly list funding plans of my in the coming 5 years. So in the first several years, I will first apply for the NSF Faculty Early Career Development Program or the Young Faculty Award Program. I will also seek the opportunity in the Summer Faculty Fellowship Program at the Air Force Scientific Research. I know this program requires a green card, so I might need to apply for a green card first. And then I will submit my proposal on the robustness and data efficiency of the reinforcement learning to the CCF program, because I'm more familiar with these topics. And in the first several years, I will get to know and get familiar with my collaborators and faculties here at UCF. And with that connection or collaboration in the following years, I aim to submit some proposal on the applications of reinforcement learning with different areas together with the UCF faculties. And I also aim to submit my proposal on the trustworthiness of AI to the CCF program. I will also seeking fundings from Department of Defense or the industrial companies. So basically, I will mainly submit my proposal to NSF, including the Computer and Information Science and Engineering and the Directorate for the Engineering program. I will also seek fundings from DoD and the industrial companies. So finally, the teaching plan. So during my PhD period, I served as a teaching assistant in courses including detection and estimation, machine learning, and digital principle. So I'm actually very comfortable to teach courses related to a foundation of the electrical engineering, mathematics, or machine learning. So here at UCF, I'm able to teach courses like randomness, random process, machine learning, optimization, information theory, or detection and estimation. I will also aim to develop my own courses like advanced reinforcement learning or advanced deep learning or advanced topic in optimization or statistics. Okay, that's all for my presentation. Thanks for listening.
Yeah, I guess start.
Can I ask a question from the non-AI people?
Sure.
And so trustworthiness is a big word in the AI these days.
Yes.
Especially after the ChatGPT. Is there any way to mathematically define this? And I'm always try to puzzle about this. And also, is there any like concerted effort within the community try to come up with like a kind of common framework to define that term?
Yes. So as you can see, the trustworthiness has many different aspects. For some of the aspects, it can be mathematically formulated. For example, the robustness, we can use the robust reinforcement learning. For the data efficiency, of course, we can study the sample complexity. And for the privacy, especially the differential privacy, there has been a mathematical framework and a formulation for this problem. But for more general other aspects like explainability or the fairness, it's kind of very difficult to build such a mathematical formulation of this problem. And actually, most of this works on the on this explainability or fairness part is more heuristic or experimental. So there's no mathematical or theoretical guarantees or formulation for this. So one of my research goals is to develop the mathematical or theoretical formulation for these topics and to provide them with a theoretical guarantee and from the very fundamental of these issues.
So it's a bigger thing.
Yeah.
It's not a simple thing.
Yeah.
Mixture of many things.
Yeah. I need to collaborate with experts from many domains. Yes. Yeah, this one is like the ultimate research goal of my research, or even the whole AI community.
So one of the aspects of explainability that you mentioned is the constraints. For example, you're able to satisfy constraints. So that gives an aspect of explainability, which you're saying you're doing.
Yes.
Yeah, the TMLR paper, I guess.
Yes. So basically, in this paper, we study the robust reinforcement learning with safety constraints or constraints on the cost or resource. So basically, it shows that we can develop a robust algorithm that satisfy all these constraints. And hence, it's of course the safety or the constraints is one of the trustworthiness of artificial intelligence, especially in the fairness. We also consider the constraints on the fairness. So basically, although they have different aspects of this trustworthiness, there are many potential ways that we can develop research on and solve this problem to develop the AI system. Okay, thank you.